just let, yes, and I will just launch the VOOV application.
Okay.
So,
okay. So so this presentation was requested by ECSN, and the purpose is more of a introduction to the topics on the research that I've been conducting. It's not intended to go too deep into the three topics I was going to talk about, but I'm trying to go over three different magnetic energy conversion research topics that I'm working on in Portland, Oregon. So the three topics that I'm going to talk about are magnetic gearing, resonant ocean generator applications, which are related to magnetic springs, and electrodynamic wheels. These are the three research areas that I'm primarily conducting research on. I'll mainly focus on the magnetic gears topic, actually. Okay, so magnetic gears, why magnetic gears? So mechanical gears are used extensively in industry. They're used in wind turbines and electric drills. This is a Planetary mechanical gear, and then there's cycloidal mechanical gears used in robotics, higher gear ratio. And mechanical gears have been around for a long time. This is one on the left here from the 1st century BC. And so we've known about mechanical gears for a long time, and they've been developed over centuries to a refined level. We didn't invent mechanical gears. This is a grasshopper that has a gearing system in it. So they're used in a lot of applications. They have drawbacks though, reliability. There's physical contact between the gears. They require lubrication and maintenance. They have vibration and acoustic noise issues. And if you over torque them, they can fail potentially catastrophically. And particles come off them, causing increased wear, and therefore the life is limited. But we use mechanical gears in many applications. Why is that? If you look at it's a bit old now, but if you look at the Toyota Prius, the motor for that is around 45 Newton meters per liter, whereas the Nabtesco cycloidal gear used in robotics is 371. So you can see a significant difference. The motors are limited by electric loading and magnetic loading, thermal issues, whereas the mechanical gear is limited by the mechanical forces. And so therefore we often couple the motor with a gearbox to make a more compact drivetrain. The applications that I've got research funding for on magnetic gears is related to ocean generation and wind turbines, primarily, as well as some electric plane work. And so the interest in for ocean generators is that the generator, this is a turbine from Verdant Power. the turbines are located in the sea, and so therefore maintenance is very, very difficult. And so you want gear systems that do not require maintenance, but also you don't want them to be very large in size, excessively large. So with the ocean, the speeds are low and the torque is very high. So there's reliability concerns, and so magnetic gears could play a role in particularly in applications where reliability is very important. So let's take a look at why that's, I can't get rid of this. Let's take a look at coaxial magnetic gears. There's a number of different magnetic gear topologies. I'm just going to talk about coaxial magnetic gears as it's the most popular and most highly researched. And so I'll explain its working principle in a couple of slides. But the coaxial magnetic gear became popular following a Toller paper in 2001 from Sheffield. But the interesting thing is that the first patent on it was in 1968. But nobody really worked on it until it was demonstrated by Toller and Howe that you could get up to twice the torque density of a direct drive motor. So how does a make this little thing go away down here? How does a coaxial magnetic gear work? So if you look at this diagram on the left here, it contains 3 potential rotors. They've got the inner rotor with the P1 pole pairs, an outer rotor with the P3 pole pairs, and then in between you have these ferromagnetic segments. And in this picture here, there's N2 of them. And so the P1 in this example, the P1 inner rotor creates 4 pole pairs, and that will create a 4th harmonic. And then the modulator contains, in this example, 14 segments. So the magnetic field will pass through the modulator, the ferromagnetic pieces, and the harmonics will add and subtract. So you'll get 14 plus 4 is 18, or 14 minus 4 is 10. So if you put 10 pole pairs on the outer rotor, you can then get a coupling between the fields and therefore a speed change. And in the case of all 3 rotors rotating, the speed relationship is given by equation 2. In order for this to be satisfied, you need to choose the pole pair combination to satisfy equation 1. And usually you make the modulator have the higher number of slots that will maximize the torque. So if you hold one of the 3 rotors stationary, then you get a gear ratio given by equation 3. For example, in this case, the outer rotor is stationary. Maybe I'll put this up here. So in this little example, we get a gear ratio of 3.5, which is quite a low, but it's an example. And it's really quite remarkable if you think about it, because you're getting this speed change without any physical contact. No gear lubrication is required, and if you over torque it, it would pulse slip, but the gears would not catastrophically fail. So this has some unique potential benefits, but the question is, can you make the magnetic gear competitive in terms of performance to a mechanical gear? and that's been my my focus has been building magnetic gears to try to show that the torque density can become close to a mechanical gear. I think that the best way of visualizing how magnetic gear operates is maybe like this. This is an axial version where you've got rotor 3 has 12 pole pairs, and then in front of that you have these 16 ferromagnetic segments. So if you were to imagine looking in towards these ferromagnetic segments, you'd see the picture on the bottom right here, and you can note that there's 2 red, 2 green, 2 red, 2 green, and so on. So you can see that there's 4 pole pairs, 16 minus 12. And so if you rotate one of the rotors, you'll see a speed change. So this is looking through the air gap, but of course, as we know as electrical engineers, the magnetic field goes through the ferromagnetic segments, and so that will also see this harmonic being created. So there's different researchers have studied different magnetic gear topologies. I focused on the flux focusing magnetic gear with this outer rotor being flux focusing and also an inner rotor. But then I moved on to look at mainly Halbach magnetic gears. The reason being that the Halbach has lower additional harmonics, creating lower losses, and also I believe that the flux focusing, for example, this outer rotor, it's mechanically difficult to assemble, and mechanically difficult to hold together. So I've changed my focus, my research focus to Halbach type magnetic gears. So I'm just going to talk about 3 magnetic gears I recently, or 4 magnetic gears I recently built for the Department of Energy wave energy generator project that I had. One of them was a 5 kilowatt dual stage magnetic gear. So the idea was to get higher gear ratio. So in this case, we got 63:1 gear ratio. So this was achieved by using 2 stages of magnetic gear to connect together. One of them was 6.67 and then the other was 6.5. And the input speed is very low because it's from, the idea is it's from a wave generator. And initially we proposed to make it hermetically sealed. And so the idea here was that the modulator, the ferromagnetic modulator would be fixed, and then the outer rotor would rotate around it. And in that way, the modulator could be sealed and create a hermetic seal for the entire generator system, and make it more reliable. But by doing this, it meant that we had to design both magnetic gears to fit together, and this caused additional risk in terms of testing, because we couldn't easily test each stage individually. And so in order to reduce the risk of failure of one particular magnetic gear, we decided to do it in 2 stages, with the understanding that they could be connected later. And so this is what we came up with, the stage 1 and the stage 2, and then this is the generator. The generator was an off-the-shelf generator, and so after much design, PhD student who recently graduated, we designed these two magnetic gears. Stage 1 used this Halbach configuration on the outer, and then this we called it flux concentration on the inner, with these ferromagnetic pole pieces with the magnet insert, and then this had a 6.67 to 1 gear ratio. So the outer rotor was rotating and the modulator was fixed, because of the idea of this hermetic sealing. And then the stage 2 shown here used a unique magnet arrangement which improved the assembly ability to assemble it. Most of this work is about to be hopefully published. So in order to choose the design for the stage 1, we did a lot of parameter sweeping of the radii. This just shows an example of the torque versus torque density. This is 2D, so it's quite high, shown here. And so we selected the value that had the smaller radii, but met the torque requirements. And then, after the parameter analysis, we also looked at deflection. These modulator pieces can deflect if they're too thin. And so we used the magnetic forces to then calculate the mechanical deflection on the modulator segments. And this on the bottom left is the radial forces. If you choose the modulator segments to be an even number, 46, for example, here and 38, then the radial forces are even, and this reduces the deflection and can make a quieter design. And so that's recommended. This is the assembly for the inner rotor. This is the modulator. Here we used you can see we used bridges in a bridge on the ferromagnetic modulator, and then inserted in between each one was garolite support to hold everything together. And end plates were also garolite in order to try to reduce the losses. This is the magnetic field measured for the inner and the outer, and the harmonics that we obtained. And then this is the experimental testing of the stage 1 with torque transducers on both sides, and gearboxes on the motor and generator side. This design had some difficulty with the torque measurements. This is on the low torque side, and then this shows the operation of the step change in the torque for the inner and outer until it pole slipped. And then the power loss is shown here as a function of input and output speed, and then the efficiency map. And then this shows some of the experimental results. So after there was some discrepancies with the which is discussed in the submitted papers in the measurements, but overall we got a pretty close result. The volumetric torque density was measured to be 268, which is I think quite high, Newton meters per liter. And this is active region, not including the mechanical parts. And then the second magnetic gear was this stage 2. So this is the higher speed one, And we used this kind of unique arrangement where the magnets were slightly changed in shape. So the idea here was that this would allow the assembly to be more easily achieved, because you first can put the radial magnets in. And so you place all of those in first. And then it turns out then the azimuthal magnets easily slot in. So it's actually the assembly process for Halbach is actually not that difficult if you put the radial magnets all in first. It's not a good idea to go one at a time. That's really difficult, which is what I used to do. So you should always put in all the radial magnets and then the azimuthal, and then it's really not that difficult, relatively speaking, to assemble. But with this approach here, there's some spacing, and so therefore, because the magnet tolerances is not there's often a 0.1 millimeter magnet tolerance. If you have this design, then the magnets can slot in even if there's a tolerance in accuracy. We applied for a patent on that. So we in order to design this, we did sweep of the mass torque density versus the volumetric torque density. This just shows examples of different design spaces. This is 2D first, and then we did 3D. I don't want to spend a lot of time on all of the parameter analysis. This shows the inner rotor assembly, which I think is kind of like I said, unique, the shape. And so again, you can see on the left, we just assemble the radial first, and then the azimuth will just slot in relatively easily. And then this is the assembly process. You could use it. You could use a lathe to assemble it. We used this assembly jig. And so this is the inner rotor being slotted into the modulator. Again, we use Garolite rods to support the modulator, because then you have lower losses. And then again, in this design, the PhD student had a failure by when characterizing the magnetic gear. The student didn't ran the motor too fast, and we believe overheated it, the magnetic gear. So the measurement before overheating is shown in red, and then the measurement after overheating is the black. Fortunately, we overspecified the design, and so it still reached the required torque requirement, which was 180. This shows the torque ripple, which is very low in this design. This is step changing the torque. And then this shows the results. So we measured 188. We were required to get to 180 for this DOE design, Department of Energy design. The original was 227. So the torque density went down to 236 Newton meters per liter versus the 285, which we were hoping for. You can note that the efficiency is significantly lower than expected, and I'll talk about why I think that is in a little bit. And then also when you add the generator in there, so what the generator has a 15 Newton meter per liter torque density, so it's quite low. When you add that in, that makes the total 66. So you can see it really brings it up versus just so the actual torque density depends on the generator site torque density as well, the overall torque density for the magnetically geared system. This shows the two stages connected together. And we also added liquid cooling onto the stage 2 because of the higher speed. There was some concern about the overheating, so a jacket was added on there because to make sure that the magnetic gear didn't overheat. and then this shows the change. So on the high speed side, you can see the torque is much lower than the low speed side. So we've got the 63-to-1 gear ratio. And then this shows the total power loss of the dual stage and the individual stages, and then the efficiency map for the dual stage. I think I can. This shows the dual stage running. You can see the stage 1 here. It's very clearly seen running because of the outer rotor rotates, whereas on the left here is the stage 2, which you can't see operating because the outer rotor is stationary. It's the modulator in the inner. So you can clearly. So I hope you should be able to see that there's a significant speed change there. So 63-to-1. So that shows it works. So overall, the top for this is for the dual stage. The torque density was around 228 newton-meters per liter, and the active mass torque density is around 42. The efficiency was significantly lower than expected, than we calculated, and so we believe most of this discrepancy that we did not expect was due to this in-plane eddy current loss, which I'll talk about. I've not seen anyone study this before, actually. We have a paper that's under review that talks about this phenomenon. I'll talk about a bit. And then down here is the example of a Sumitomo planetary gear. This is a mechanical gear. You can see that this is the gear ratio is 59. It's close to the 63 that we used. And you can see that the volumetric torque densities, range from around 340 to 267. The interesting thing is the mass torque density is around 20 to 30. Torque density here in the top for the magnetic gear is actually the active, so it's 40. But I think what's interesting is that if you include the structural, which we didn't include in this table, which we didn't optimize the structure. Okay, so I think I was at this point. I was trying to say that I think this is what's exciting is that if you look at the mass torque density of the magnetic gear for the active region, and compare that to the mechanical gear for this Sumitomo, at least, which is sort of a leading gearbox manufacturer, you can see that it, it's if you had twice as much material for the structural, it would be competitive with the mechanical gearbox. So I think in terms of mass torque density, the magnetic gear is could be competitive. So I also worked on a larger magnetic gear that was where we tried to make it up to 50 kilowatts. It was going to be 2 stages, but we only built the second stage due to funding limitations. We've received some more funding for more magnetic gears, but in this one we just designed the second stage, and we changed the design to use circular rods, as shown in the bottom right, because this is a lot simpler and lower cost to manufacture. It's a lot cheaper to make circles than squares, so and the performance doesn't degrade that much. We also tried to reduce the losses by having a higher number, improving the harmonics by having more number of segments on the inner for the hellback. It turns out the cost wasn't that much different, and then we also laminated the magnets to try to also reduce the losses. We did a lot of parameter sweeping on this one as well. This is just showing some pictures of some of the analysis where we we looked at the mass torque density on the y-axis and the volumetric torque density on the x-axis. These values are all 2D, so and then we did 3D sizing as well. But I won't show all of that. And then this shows a comparison between using 4 and 12 segments for the inner rotor. I've not seen an inner rotor a magnetic gear with this number of segments, and the reduction in the harmonics between 4 and 12 is quite significant. And then we also laminated the magnets to reduce the losses. You can see that the left is the solid magnets, and then the right is laminated magnets. Loss analysis, sorry, the current density analysis here. This also improved the efficiency performance. The loss comparison is quite significant. 269 versus 38 watts for the inner rotor, for example, here, and the total loss went down significantly as calculated. So we thought that we were going to improve the performance further with this design, and we also, in order to get the higher torque, we used a unique dual stack design. So we basically have 2 magnetic gears stacked together instead of having a larger diameter. The reason being that the cost of increasing in diameter is quite high versus keeping the diameter smaller and having multiple stacks. And so we did it this way. And so thermal was an issue that we checked and redesigned to make sure that the heat could flow out. And so this was a thermal analysis that was conducted to make sure the magnets didn't overheat. So the losses were inputted in to calculate thermal. And then this shows the one of the inner rotors here and the outer rotor on the right, and then the modulator, the 2 sets of modulators with the garolite end plates and support rods. And this shows the assembly. And then this shows the magnetic gear on the test stand with the 2 torque transducers. And here in the bottom shows the some results from the torque step change. And I have a video here proving that it works. This shows the magnetic gear running. This is on YouTube. And so we measured the torque on both sides and measured the efficiency. So this shows the power loss calculation, and we used a curve fit, and then from that we created this efficiency map. And then the losses were still more than we expected, and we discovered that this in-plane eddy current loss was one of the reasons for the increased losses. And then there was further losses on the support rods that we did not expect. So I'll talk about that here. So the in-plane eddy current loss is loss caused by the axial field. So most electric machines don't have a very large BZ field, but the BZ field and the axial field in the magnetic gear is quite high because of the modulator goes between high reluctance and low reluctance, so that the field is often forced axially outwards, creating a large BZ field, leakage field, and that causes a significant reduction in edge effect, larger than a regular motor. And then because of the leakage field, it means that the laminations see a changing field in the z-axis, which is not normally accounted for. And so even though the laminations are laminated, even though the modulator is laminated and the magnets are laminated, there's a circulating field, circulating current created from the Z field, which is not normally calculated. And so we discovered that this was one of the significant causes of loss in the magnetic gear, and I don't think that's been reported on before. And then, and so this also caused problems on the outer because we had this outer lamination. And so the losses on this this was laminated on the outside, and that therefore then created losses on this outer, which we did not expect. And so because of this, you can see there was heating on these, this is a thermal camera image, heating on the outer laminations. And it was also on these support rods, there was much higher than expected loss because of the current created, circulating current from the BZ field going through these rods, and then current circulating. And so this played a role in adding up these additional losses shown in yellow that we originally did not predict. So that explained some of the reasons for the larger losses than expected in this design. But so we still we got 96% for this stage. This one we were expecting 98. But there we did we did achieve the torque requirement. So this sort of summarizes some of the prior magnetic gears as far as I can, so as far as I'm aware of, in green dots here. And the three magnetic gears I've presented are the red dots. The black are mechanical gears. It depends on the manufacturer. The ones that are lower torque density are from Newgard. This is a very high performance, a high reliability gearbox. And then there's Sumitomo have had these higher torque densities here. And so depending on the life expectancy of the gearbox, that can also play a role in the volumetric torque density. So it looks promising, in my opinion, the potential for the torque density to be competitive. The future for the magnetic gears, I think still more work needs to be done on improving efficiency, particularly in-plane eddy current loss. In my opinion, other people have reported on high efficiency magnetic gears, but the torque, I think we need to have high torque density and high efficiency. And more work, I think, needs to be done to do long-term testing of the magnetic gears, and then off-the-shelf type of controllers for magnetic gear machines need to be available to run on drivetrains and drives. And then we at my research group hopes to do testing of the magnetic gears in water tank and ocean generator in the next 4 years. Another area of magnetic gear research is in electric aircraft. NASA actually has a research program on magnetic gearing for electric aircraft, and I worked on that for a little bit. This is the electric planes have completely new possibilities in design. You could have many smaller motors rather than just a couple of big ones, and that could improve the lift to drag ratio. There's really a lot of different possibilities, and one possibility is to use magnetic gearing for the thruster to replace the mechanical gearbox. And this is an example of electric plane magnetic gearbox that we also built. It had a target torque density of 53 Newton meters per kilogram, including all of the mechanical structure. And so this left shows the carbon fiber design, but we, due to budget limits, and time, we made it out of garolite. And so this is 12.4 to 1. We haven't shown the publication for this yet. Okay, so that's magnetic gears. So I'll try to go over these other two topics a little bit. I've kind of lost track of time now. So the second topic is resonant ocean generators. What is a resonant wave energy converter? It's really quite interesting. If you think about the sea as very low frequency, and so how do you, if you have a small device, this is CorePower, and then these guys on the left here is from Aqua Harmonics, that they won this DOE Wave Energy Prize. The generator, if it's not big, is not going to naturally resonate with the low frequency because of its smaller size. So in order for a smaller generator to resonate and maximize the power generation, a way of reducing its natural frequency is required. And it turns out one way of doing that is to have a negative stiffness spring. So magnetics can have a negative stiffness. It just basically means the magnets are repelling from each other. So this is an example of CorePower. They're using a mechanical spring arrangement in here to create this negative stiffness. So the blue is a negative stiffness. So as you go, as you increase in position, you get an increasing force. And so when you add this negative stiffness blue line to the device, the red is the natural spring arrangement for something. Because if you think about it, if you just move something up and down in water, it has a natural resistance to it, and so you can add this negative stiffness to change its slope, and therefore allow it to couple to the low frequency wave motion. So in order to do that, though, the frequency of the wave is constantly changing, and so over time it would be good to be able to change the stiffness as well, this negative stiffness. So the mechanical spring is very complicated. Actually, you need this unusual a spring arrangement to create negative stiffness for mechanical springs. It's quite large actually, and complicated. So I was looking at, could we create a negative stiffness spring, rotary spring, where we could vary the stiffness. So we looked at different magnet arrangements, and the one shown in G was selected. This is in the red here. And you can see it creates this remarkably linear stroke length. It's a torsional spring. Only has 45 degrees, so it needs a gearing system to increase its stroke length. That's the disadvantage. And so we in order to change its stiffness, you actually shift the spring magnets in this design, and that allows you to change the stiffness from a positive to negative, and anywhere in between. And you can also, if you center it, you can decouple the spring from the wave energy converter. And so we, in order to validate this design, we built a small version of this. It's only had 45 Newton meters. We've got a new one that's 800 Newton meters that we're about to test. And so this shows the inner and outer rotor, and then this shows the experimental setup. And we got relatively close measurements. And then the idea here is that you would have this mechanical spring, which represents the wave energy converter, and then you have the magnetic spring. So you adjust the magnetic spring to be negative stiffness, and then when that's connected to the wave energy generator, it reduces the overall system stiffness down. To allow it to resonate with the waves. And so we modeled that. We modeled the wave energy converter as a positive stiffness spring, and then we have a negative stiffness spring. And then by applying a frequency with the stepper motor, we can tune the stiffness for the magnetic spring stiffness to create resonance. And then, so this just shows you an example here where we have this resonant ratio of the output angle to the input angle. And so on this plot on the top left, with the x-axis is the frequency, and that the y-axis is the resonance ratio. And so you can imagine that the frequency of the wave is at 1.5, and so by tuning the negative stiffness to be minus 38, you can create the resonance 8-to-1 ratio, and then you can, depending on the wave frequency, you can change the stiffness. And the right shows the example measurement, and when it gets about to here, it's too great a degree. It gets to over 300 degrees stroke, and so it can't go higher than that. So the idea is then you have a generator connected to that, and that's the last part that we haven't added in here yet. And then you can take off power. And we're working with Sandia National Laboratories with the controller. They've developed the controller system for this. And so we need to add the generator on here so that then we can take off power and demonstrate the ability to take off power. So wave energy, in my opinion, you need both the magnetic gear, and then you need some sort of resonant spring system with negative stiffness in order to potentially make it cost effective. Okay, and then the last topic is on maglev transportation. This is something I've been working on for a long time. I have a bunch of new papers on this soon. The idea is that I've been looking at is this electrodynamic wheel concept. So the concept here involves rotating magnets. In this case, in this picture here, you can see a Halbach magnet array, and then this is rotated over a conductive track, such as aluminum, thin sheet. And then this induces current in the track that can create, due to the rotation, it creates a lift force. And then a thrust force is also created. The thrust force is dependent on a slip, which is the relationship between the circumferential velocity Vx and the translational velocity of the vehicle. And so the idea here is that could you create a maglev system where the track is just passive, like high-speed rail, and stable as well as important. And so it's rather than having a motor along the track, which is what a lot of the maglev systems use, or a wraparound track, which makes very difficult and expensive to change directions. If you could have a flat track that's like high-speed rail, then you could potentially make it as cost-effective as high-speed rail, and you could potentially integrate it into existing rail tracks. So it would allow existing rights-of-way to be used with maglev. So that was the idea here. You could use a linear induction motor on here, but the problem with the linear induction motor rather than the magnets is that you would then need back iron, and then you wouldn't get the lift. And then you also have very low power factor if you don't have the back iron. The disadvantage is you need an onboard power source to rotate the magnets. So I built lots of different setups on this. This shows an example of very early one. This is a Halbach rotor, and I tested it over this with this wheel here. So rather than the track, rather than the vehicle moving, the vehicle was stationary and the track moved. This allowed the forces to be validated. Later design had a flat track here with the 4 wheels rotating and going along the track. I used different track configurations to try to create stability. I've been working on this for quite some time with a number of PhD students, and we've come up with some new designs recently. It's been a lot of time doing the analytic modeling because it's actually very difficult to calculate the forces when you're rotating something and translating it in 3 dimensions. Surprisingly, it's a really difficult analytic problem. It creates very interesting math. So this just shows examples of some of the analytic modeling that I've done to develop the tools to calculate the forces. And we got good matches there. I did this at in Charlotte, North Carolina. And so the ultimate goal is to be able to put this track on existing rail system. Then you could potentially have a maglev system on existing rail, and that in my opinion would make it potentially cost effective. I don't, especially in the US and in many countries, I don't see maglev new tracks being created. And so this, if we could come up with a way of putting it on existing rail or highway systems, then maybe this transportation could be used in place of aircraft, because I don't know how we're going to be able to fly long distances without creating pollution. This is a challenging problem. So maglev may play a role if we can make it cheap. And so that's all. I could spend a lot more time talking about those other 2 topics of maglev and magnetic springs, but I'm going to leave it there. I'd just like to thank all the PhD students and MS students and undergrad and postdocs that I've worked with, and some of the financial support from these funding agencies and software companies is greatly appreciated. That's it. Does anyone have any questions, thoughts?
Thank you, Jonathan. So questions time.
Hi, yes, thank you very much for a wonderful talk here. I just had a couple of small ones. I was wondering if you could comment a little bit about the maybe some of the manufacturing challenges you encountered when you expanded some of those Halbach arrays from the standard kind of 4 to 12 size arrangements, just between speccing and magnetization to installation. If there was any interesting things you found about that.
The higher number of segments. I didn't actually do that. My PhD student put those ones that you're talking about, the 12 segment one. That's a good question. We didn't use this. We didn't use the in this 12 segment. We went back to using the individual pieces. I don't think it didn't seem to pose any major issue. What we did is we used a ferromagnetic back iron here, and then that greatly helped with the assembly, because the magnets, the radial magnets, want to attach onto that. So my understanding was that the radial magnets were put on first, and then there was a assembly jig used. So we have an additional assembly jig that was used to line up the magnets, and then they could be slid into the slots. And so if you have an assembly jig, and then you do have, if you have this ferromagnetic back iron, then the assembly is not that difficult. The trick is that you don't want to ever put each magnet in one at a time. You want to think about the individual magnets directions and put them in the right order. I wouldn't recommend using any. If I were to design another one, which we plan to, I'm going to try not to use any steel backing. The torque did go down a little bit, but I thought that was worth the benefit of making assembly easier. However, the losses, if you use this steel backing, even if it's laminated, you still get these in-plane eddy current losses. And so that really negatively affects the performance. So I would try to avoid any steel, which is what some of the magnetic gears by NASA, they didn't use any steel, and also used Halbach. I didn't use that because of weight wasn't as critical. But in hindsight, to reduce in-plane eddy current loss, I think it's a good idea. That was a long answer.
Thank you.
Any further questions? Yeah, Jonathan, I have a question about the magnetic gears. We do not see a lot of work on electrically excited, or to be honest, I have never seen work on electrically excited magnetic gears. Is there some work done on that?
Oh, you mean replace one of the like, you could replace the inner rotor, for example, with a stator?
Yes, with yeah.
I mean, yeah, I mean, there's lots of papers on that type of thing, but I mean, it depends. There's vernier motors, which are one type, but other people have been, which is promising, but some other researchers have looked at replacing one of the rotors with a stator. However, there's a number of papers that convincingly show, in my opinion, that if you replace one of the rotors with a stator, the torque performance is no better than a regular permanent magnet motor. Because if you think about it, if you replace one of the rotors with a stator, then you have two air gaps, and you have this modulator. And so whilst you do have this magnetic gearing, there's a number of papers that have shown that the torque density is then no better than a regular permanent magnet motor.
Yeah,
lower power loss. So but people keep publishing on that. I just don't see the torque density being very good. So I don't understand the benefit, other than maybe you could have the two rotors rotating, and that would allow you to have a different gearing if you have two different inputs.
Yeah, I see what you mean, but I was talking about replacing one of the, maybe, or both, by electrically excited once, I mean, using DC current, supplied using DC currents.
DC.
Yeah, you can imagine that you can have a winding arrangement allowing to change, for example, the number of poles. The goal is to have a variable gear ratio magnetic gear.
Right. Yeah. Yeah. That's I mean, yeah. If you could, you would also need to have some way of transmitting the power to the rotating rotor as well.
Yes, that's right.
I just don't think that the torque density would be very high, and I think that the benefit of the magnetic gear is that you don't have to have any power on here, and you can get the speed change. So I think the challenge is to show that if you did have the DC winding on there, then you could get a torque density that's better than a regular motor. Because if you can't, then you might as well just use a regular motor.
Yeah, I agree.
You know, so that's the challenge. And you know, the early magnetic gears were only 100 Newton meters per liter. That's really not that's still not good enough, in my opinion, to you need it to be like 250 to be, you know, really competitive with a mechanical gear, the torque density. So then, you know, then it's like 5 times a direct drive motor, the magnetic gear. If you can do that, then it has some competitive advantage. But if it's only the torque density is 100 Newton meters per liter, it's not really high enough to justify the benefit. I don't think.
Okay, thank you.
Yeah,
I do have one more question. Thank you so much, Jonathan. This is Pierre. Thank you so much for the wonderful presentation. Very, very interesting.
Oh, thanks.
I just had the question of what would be if you, in the first part of the talk there for these things with a double stage magnetic gear, if you take the overall system, what would be your torque density, including not simply from the active parts, but from the whole kind of? I know that's difficult because you have joints and whatever, but if you would take kind of each part with its housing, and then you would is it things that are competitive, or actually at this stage it's not, we are not there yet?
Well, there's only so much I can do with PhD students, but we only calculate in the yellow here. We only calculate the torque density for the active region.
Yes.
So it would be quite a bit lower than this, but it wasn't optimized for this is the dual stage torque density. What I think's interesting is the mass torque density. So we didn't actually weigh the actual I didn't calculate what or weigh the actual magnetic gear structure, but you can see this is around 42. So if you look at the mechanical gear, which did include the mechanical structure, it's about half. So I mean, if you assume that the mechanical structural parts is equal to the active structural part, then you know this would be half, and then it's competitive. Yeah, I think more work needs to be done on that. I think also there's some work from NASA that's looked at the mass torque density in particular and shown that it's close to competitive. I think if you're, you know, it's getting closer. It also depends on. I also showed this comparison at the end here, where it depends on the manufacturer of the gearbox too. The new guard, if you compare with the new guard, then the performance looks a lot better. If you compare with Pacific and Home Automation, then they have very high torque densities, like 500 Newton meters per liter, but then they're not designed to last very long. So it's very hard to know which ones it depends on the manufacturer and how long they last for. So it's not entirely clear what's but I think they're not far off.
Yeah, excellent. Thank you. Yeah.
Any further questions? If not, I think we will stop here. Thanks, Jonathan, because it is late at Portland. And I apologize for what happens during the first part of the talk. I was naive, thinking that giving all the rights to people to join. Next time,